Hello, my name is Daniel Schöler. I'm the founder of Deep Foundation Design LLC, and in this video I want to make a commentary on a potentially hazardous mistake in the Eurocode 2, the German or international DIN in 1929. No, this was where the inflation was 1992, 1-1. So let me explain you what I mean. There is a potential, obviously, that I made a mistake here. However, I will explain briefly and without further ado what I mean. And I ask if you feel interested, or if this is part of your responsibility to take a look at this, because I think it could be potential hazardous to ignore this mistake or this potential mistake. Okay, bear with me. So this is the relations that we can use in the Eurocode for the design of steel and concrete structures. So I personally have to do a lot with piling foundations. So when we talk about CFA piles, then for example we have this relations between the stress and the tension that we use, and we have a epsilon YD. This is where the elastic part of the deformation of the steel stops, and then we enter the plastic phase. And to make it simpler for us to use this, especially if we have a huge volume of calculations that we do, the norm allows us to use this simplified version of this relationship to do our designs. And so basically after epsilon YD, we can use the FYD for any sort of epsilon that comes after that. Okay. Now, when we take a look at how this can apply, I had a project recently where I was working on some foundation piles, and I was thinking about, okay, what happens if I use these sort of piles on tension, for example, for a big bridge where we have these anchorage points where we anchor the big cables, for example, for like a hanging bridge. And so I was taking a look at the potential distortion pictures. So let's say we have just a stress, like a pile that we just pull, right? So we don't have any concrete pressure or concrete component. We just have the steel component because the concrete, it will just rips, and then we only have steel. And when we have a situation like this would be the distortion that I would expect here. Obviously, when we look at it and we do the equilibrium around the centroid of the pile, then we would assume that we get a bending moment of any kind that would introduce this sort of distortion. Because if there were no bending moment, it would be probably looking something like this. But obviously, since there is some sort of bending introduced and it's just tension and bending, we would expect some moment that would be introduced to achieve this. So when I did the calculations, I figured, okay, my program just says, okay, there's zero bending going on. And so I was thinking, like, what is going on? I was looking at my source code, at my programming code a lot of times, and I was just thinking, like, this must be something very stupid. Like, I must have been doing like a very stupid mistake in my programming here, and I wasn't expecting it to be potentially something that is caused by the norm. And so out of frustration at some point, I just said, okay, just plot me all the steel forces and their respective y coordinates, so that I can just like export them to Excel and see what's going on, to make like a manual equilibrium of forces around the centroid. And so when I plotted these forces, I didn't even need to do this, because I already see, well, like all the steel forces here, they're all the same. So I was thinking, like, what does this what does this mean? And obviously, like, this is something that I implemented years ago. This is not something that I questioned or something. I was just like, okay, I can use both, so I'm just going to use this one because it's easier, and I'm not going to like waste too much time thinking about what I'm using, because this is what the norm is for, that you use it and you expect that the results are going to be fine. And so I use this, and this also explains very well what's going on. If we go here, like where the mouse is, then we assume that this will be 12, and here's maybe 18. What we see is it will just return us the FYD for both epsilons. And obviously, if I have like a rebar cage and this is usually symmetrical, or like maybe it has an uneven amount of rebars, we would expect like a little bit of a difference. However, if it's symmetrical, then I would assume that if all rebar diameters are the same, that then all of the forces are going to be the same. And this is what we see in the results. So it's totally clear why this happens. And then from there, if you're then considering this, you just see that these forces are then technically all the same force. Then you already know, okay, 100% I understand that there cannot be any like mistake here. So the calculation is totally correct, even though it's totally obvious that there must be some sort of bending going on, even though we don't see it in the results because of this horizontal relation here that was introduced in the norm. So then I was thinking, okay, this is a special case, and this is it's not something that I have calculated in the practice, but what if we take a look at the normal case where we just have like a stressed, like a compressed pile? So we say 3.1, and this would be something as you would expect if you have just like a bending sort of thing, but obviously like piles and piling foundations are mostly compressed, so I would expect a distortion that more or less looks something like this. There we get some sort of bending moment, and when I was taking a closer look, I also saw here that the forces here are all the same. So I was at least sure that there is no like part of the rebar that is potentially lost. I haven't been taking like super deep into the consequences of what this means. However, we obviously know that this must be something that is obviously wrong, and this is just due to the fact that this relationship here is just constant after a certain epsilon. This is what creates this. So I was thinking, okay, maybe I can, and I don't know if this might be a mistake in my part, but what I was thinking was, okay, I can just say I will go with my eccentricity right into the middle of the centroid of the volume of the FCD, of the concrete pressure zone, so that this will not have an impact on the overall bending moment. So I can do this right now. And what you see is basically now we are here, the red dot is under the blue one. And so like the concrete doesn't have an influence anymore on the bending moment. And we see that with this situation here, we have like basically 2000, around more or less 2000 kilonewton meters, which is significant compared to what we had before that was left. So this is what I assume to be what is left out in this for this. So we go back, so 2,000 in comparison to 13,000, so it's roughly 15% mistake that we would expect if my presuppositions are correct. Then it would be something along 15% that the mistake could be. I haven't like checked all sorts of scenarios here, so if you have more examples that you want me to do, please feel free. My email address is info@deep-foundation-design.com. You can send me the requests, you can send me commentaries, you can also check if I'm mistaken maybe, because obviously like everybody does mistakes, and 2 eyes see a lot less than 20, 40, 100 eyes. So I think 15% is significant enough to talk about it and to open a discussion, and hopefully this will be very productive. Okay, any questions, any further questions, don't hesitate contacting me, and I thank you for your time and attention. Goodbye.